before we get to worksheet 3, anybody planning like trips over the summer? College visits? Where are you guys planning on? Which ones are you visiting? Very nice. Lamar, you said you're going on a trip? Nice. Very good. I'm planning a trip to Moscow. It's going to be an interesting one. But I suppose there's no sense in rushing into things. Mark's just straight face. I've said before, that's my goal. If you cannot pick up that it's a dad joke right away, I have accomplished what I want to accomplish. That being said, I don't know if I like them doing dad jokes at the beginning of school now. I feel like they're stealing my thunder. Hey, why is it that Waldo only dresses in stripes? He doesn't want to be spotted. It's not bad. Not bad. Yeah, thank you.
That's what I was going to, but I just wasn't expecting.
All right. Worksheet 3. We'll take a quick look at this, and then I have a small activity for us to do today. Remember, tomorrow is egg drop day. You can bring your stuff in and work on it, and you can have the entire class to do that. So bring in whatever you think you might throw your egg into before we drop it off above the Worship Fine Arts Center for that 2-story plunge. Okay. So worksheet 3. What numbers should we go over?
7.
7. Let's take a look at 7. If an SUV and a Prius traveling at equal speeds have a head-on collision, which vehicle will experience the greatest force of impact? Thanks, Max. See you guys. So, anybody know the answer to this one? This is less a momentum question and more a force one. Good guess. Other guesses on this one? Anybody think the semi is going to have or the SUV is going to have a greater force? Okay, so the main thing for this one is Newton's third law. I know this isn't the Newton's third law section, but it's just a short question. So when the two encounter each other and smash together, their forces will actually be the same. Because, whenever you've got two objects that smash together, the force of object 1 on object 2 is going to be equal to the force of object 2 on object 1. That's always going to be the case, regardless of who dies in the collision. Letter B. Which vehicle will experience the greatest change in momentum? What do we think about this one? The same is 100% correct, because momentum is conserved. This is where we were talking about those things with impulse. If you know the impulse of one object, you know the impulse of the other. That's because momentum is conserved, regardless of the size of the object. And letter C, which will experience the greatest acceleration?
The same.
Nope, not on this one. You might as well keep riding that horse, though, you know? It's been the right answer before. Yeah. Yep. So the Prius, absolutely. And this is the one where, this is what's gonna kill you if you're the one in the Prius. Because, yeah, the forces are the same, yeah, the momentums are the same, but ultimately it's that change in speed that's going to do you harm. Remember, acceleration is just how quickly your velocity is changing. And if you're a Prius going this way pretty fast, and you hit an SUV, you are going to stop and go the opposite direction extremely quickly. So, yeah, big acceleration means big injuries. Other questions on the worksheet here? Yes. Number 8. A billiard ball will stop short when it collides head-on with another ball that is at rest. The ball will not stop short if the collision occurs at an angle, though, if it's not head-on. In terms of momentum transfer, explain why this occurs. So, if you can imagine two billiard balls, they have the same mass. If one hits into the other, it's going to cause the other one to fly off to the right. And this one is going to come to a stop at the same position that it hit the second ball here. Now the reason for that is because its momentum is being transferred from this ball to this ball, just like we saw with Newton's cradle. You know, when one ball came down and hit the other one, that ball that was originally moving came to rest, and that momentum got transferred. The same thing occurs when you play pool. Now, if, you know, this does not hit head-on, if it hits off to the side, you're not going to get the same effect. And I'll just demonstrate this. I'm going to run and get the Newton's cradle thing. So yeah, just like before, if we let one go, this ball that I originally pulled back stops after it hits the others. But if I somehow make it so it hits at a glancing angle, you know, I guess it might not work quite as well. Yeah, not all the momentum gets transferred. And so what ends up happening then is the original ball that was moving is going to keep moving. In order for it to transfer all of its momentum to this one, it has to be a direct collision. If it's just a glancing blow, then this one's going to keep moving, probably up in this way a little bit. It's going to maintain some of that momentum. So there's a 6-paragraph long way to answer that question. The main thing is if you're not hitting it head on, not all the momentum's going to transfer. All right, what other ones should we talk about? Number 3. This is a fun one. And by fun, I mean terrifying. So the interesting thing about this one is we've got 3 things that we have to consider. We've got 2 people, and we've got a raft. Usually, we've got just 2 things, but now we've got 3, and we've got a before and an after. So there's a lot of stuff that we have to take into account here. But the good news is that if you start this problem like this, you will find your way to the solution. So let's just start it out like this and see where it takes us. Now again, there are 3 things that we have to consider. There's a raft, and there is a 50-kilogram person and an 80-kilogram person. So I'm just going to write this out. It's going to be long because we're going to have 3 momentums on both sides. So this will be for the raft. This will be for the 80-kilogram person. This will be for the 50-kilogram person. So that's what our long expression would look like there. The good news about anybody tell me what the good news about all this is? That's true, and that is really good news. The best news about it, though, is sentence number 2. The raft is originally at rest. So that means this goes away, and this goes away, and this goes away. Because if the raft is at rest, the people in the raft are at rest too. So all we're left with is the information on the right side. And we're ultimately looking for the velocity and direction of the raft. So hopefully we've got the rest of this information, and we do. The only thing we have to do, though, is we have to make sure that we set one of these directions equal to negative, because these two divers are going off opposite ends. So we have to pick which one of those is going in the positive and which one's going in the negative direction. So what I'm going to do is I'm just going to say this guy, the 50 kilogram person, they're going to jump off in the negative direction. So they're going to be diving off of that raft, both with a velocity of 3 meters per second. So let's just see how this shakes out here. So this is the entire left side of the equation. The raft is 180. Of course, the mass of the 80 kilogram person is 80. And this is going to be the positive direction. So this is positive 3, because it says both swimmers dive off with a velocity of 3. And there's our equation. Except I got to add velocity in here. There we go. So we just have to get these numbers on the other side. We'll see what happens. So 80 times 3 is 240. And then this is 150. So 240 minus 150 is going to be 90. So if I want to figure out that final velocity, then I'm going to move this 90 to the other side. That makes it negative. I guess I don't need the calculator for this. So then divide both sides by 180, and you get 0.5. And that's going to be negative because the 90 becomes negative when we toss it over to the left side there. So, yeah, that's how we figure out the velocity of the raft. So even when you're reading these problems that look complicated like this, where you've even got 3 different objects you're taking into account, you still solve it with the exact same equation. You still just plug in the beginning and the final momentum of all those objects, and the answer should shake out of that after a little bit of math. Questions on this one? Okay. What else should we talk about? Number 2. Yeah, this is a long one, isn't it? Okay. So it looks like we are shooting a gun into a block of wood. So the bullet had a mass of 50 grams. The wood and its cart had a mass of 10 kilograms. After the shot is fired, the cart, wood, and bullet moved at a constant speed, traveling 0.8 meters in 0.4 seconds. So from this, we have to find the original velocity of the bullet. So before we try and make sense of all this, can we at least figure out what type of collision we're dealing with? Is it elastic and bouncy, or is it inelastic and sticky? Inelastic, yeah, because the bullet's burrowing into the wood and it is sticking in there. So we have to deal with an inelastic collision equation. We still begin like this, but at the beginning we've got 2 objects and at the end we've got 1. So what should I label them here? Probably bullet and wood. So you can find this equation on your formula sheet. This is your inelastic sticky equation. We begin with two objects. We end with one. The masses are combined, and they have just one velocity between them. So we got to figure out what we know from this and go from there. So we know the bullet had a mass of 50 grams. So if we convert that to kilograms, anybody know what we get? 0.05. Very good. So the mass of the bullet is going to be 0.05. Yep, we're going to get that for sure. Yeah, no problem. We know the cart had a mass of 10 kilograms. So the mass of the wood here is going to be 10 times whatever its original velocity was. Now, let's see. Yes. Sure. What we're trying to solve for in this whole problem is the original velocity of the bullet. Now, the original velocity of the wood is just going to be 0 because it starts from rest. So this is as far as we can get with the left side of the equation. But the right side, we can do a few more things with. Again, we know the mass of the bullet. That's going to be 0.05. Mass of the wood is just 10. The velocity of the combined bullet and cart afterwards is something that it doesn't specifically tell us, but it does give us the information we need to figure it out. Because it says, after the shot is fired, the cart, wood, and bullet move at a constant speed, traveling 0.8 meters in 0.4 seconds. So if something is going 0.8 meters and it takes 0.4 seconds to go that far, we can find a velocity out of that. Anybody do that in their head, what that velocity is going to be equal to? 2, right on the money. Because velocity is equal to distance over time. So if we've got a distance of 0.8 over a time of 0.4, that's going to be equal to 2. So now we have our equation. So all we got to do to figure this out then, so this will be 20.1. This is 20.1 here. And then from that, we have to divide by 0.05. And that should give us our final answer, which is 402 meters per second. So that bullet is moving pretty fast when it comes out of that barrel. So again, we've just got ourselves an inelastic collision here. The best thing you can do when you're looking at these problems is really just figure out which of the two scenarios you're going to be dealing with. Is it something where these objects stay apart, or is it something where they stick together at the end? And then from there you can just figure out which of those two equations to use, start plugging those numbers in, and soon you'll be home free. Final questions on this one? Anything else we should talk about? Number 4, discuss the following in terms of impulse and momentum. Why are padded dashboards safer in automobiles? Anybody want to take a shot at this one? Yes.
I just said, so like if you get in an accident, the padding of the dashboard could like absorb some of the impact, so
Yep.
you're less likely to get injured.
Absolutely. That's a good answer to that. So in terms of when you're colliding in a car crash, would you say that if you have a padded dashboard, would that reduce your impulse? Think about that while I'm erasing here. If you have a padded dashboard and you get in a car accident, would that reduce your impulse compared to it was just a very solid, hard dashboard? So what do you think?
Wait, what?
Yeah, so think of it like this. Maybe you run into the solid brick wall over there. That's going to hurt. And you'll have a certain impulse, certain change in momentum. But if I would replace that with a mattress, you're not going to hurt as much. Would your impulse change from one to the other? So remember, impulses change in momentum. So for both cases, you start with a certain speed and you end with a speed of 0. So your change in momentum is actually not going to be different. It's going to be the same whether you run into a wall that's solid or whether you run into a wall that's padded. The difference is one of them takes longer for that impulse to occur. And that is really where you can stop injuries from happening. You know, this is why all cars have airbags, because it doesn't decrease your impulse. It doesn't decrease the change in momentum of your face as you swing forward. Your face is still eventually going to stop. But if you've got that padding there, it takes much longer to do so. And in the end, that's what's going to save your brain. You want your head to take as long as possible to come to rest, so that your brain doesn't get all messed up. You don't want that to happen instantaneously. That's where those injuries can happen. So that's why padded dashboards are safer in automobiles. It's not because it decreases the impulse. It's because it makes that impulse take longer. And this kind of goes into letter B then. Mountain climbers use nylon ropes that stretch. They don't use ropes that are just solid and have no give to them. The reason for that is because, you know, if you've got a rope that doesn't stretch and you fall a good deal, that's not going to be pretty for you. You're going to lose something because there's no stretch. You're going to stop instantaneously, and you're going to, at the very least, dislocate something. But if you've got ropes that stretch, it takes much longer for that change in momentum, that impulse to occur, and you don't get hurt. So yeah, again, it's not about impulse. Impulse is always going to be the same when you start and end. The main thing is how long it takes for that change in momentum, that impulse to occur. That's the big thing here. All right, anything else you want to talk about here? Have we had enough of worksheet number 3? I think we should be. All right. I'm going to come around to get worksheet number 3 from you. Again, remember tomorrow's a work day on your egg drops. I do have an activity that we will be doing for the rest of class, though, so hold tight.